In this video, we're going to talk about some general applications of linear programming, and we're going to also talk about formulation of simple LP problems. So optimization usually refers to a set of techniques that can be used in prescriptive analytics, meaning that they're trying to help us come up with the best set of decisions in managerial decision-making process. Usually, in a typical optimization problem, we have we're trying to actually find the best or optimal set of decisions. And in order to find the best, the way that we define best or worst action is by defining an objective function. This is how we evaluate different decisions, usually profit or cost. We want to maximize profit or minimize the cost. On top of that, we usually have a set of restrictions, a set of constraints that we have to satisfy. We shouldn't violate them, right? So we should respect the set of constraints and considerations depending on the application. The optimization problem can be linear or nonlinear, and that is based on the objective function and the form of the constraints, the form of the function in the constraint, left-hand side or right-hand side of the constraint, right? In this course, we're always dealing with linear programming, where both objective function and all the constraints always follow a linear form. Just to review some applications of linear programming or linear optimization, these are some examples that we will actually consider in this chapter. The first one is a production scheduling problem, when we want to find the best or the optimal production plan, the best or the best amount of production, the best quantity of production. And the objective is either usually to minimize the total production and inventory cost or to maximize the total profit. And we have some restrictions. We cannot, we have to satisfy the demand. We don't need to, sometimes we may be able to produce more, but if there's no logic behind it, we shouldn't. If it's gonna increase the cost unreasonably, we should avoid it, right? And sometimes we may have to, there are some customers that we have to really satisfy the demand. We can't have a missed opportunity in those cases, right? So these are the constraints. We have objective function, and the decision is basically how much to produce. The second example would be a portfolio optimization, investment portfolio optimization. The decision here would be to select the variety of stock and bond, and also the amount of investment in each one of these options, in each one of these alternatives. And then the objective would be the return. One example of the objective that you can consider would be to maximize the return on investment. Of course, you may also want to consider the risk. So you may actually come up with a mix of return and risk, or you may decide to put a return or consider return as your objective and define risk as a constraint in your problem. There might be other constraints as well, such as budget constraints. So you may have limited budget, limited capital budget that you can invest, right? So that would be a case of a limit or a constraint in this example. The third example would be allocating a fixed advertising budget among different alternatives, such as web, radio, television, newspaper, and so on. So here, your decision would be how much money to allocate to different alternatives, right? So that's your decision. Your constraint can be the amount of money that you have available. Another set of constraint might be that you may have limited number of web commercial, for example, or radio commercials that you can use. You may have some administrative constraints that you may want to balance the use of different alternatives, and so on. There might be more than that in terms of the constraint. And in terms of the objective function, how do you evaluate the goodness of a decision? That depends on, in this case, it depends on advertising effectiveness. It can be based on, it can be based on the cost. It can be based on the reach, the number of people that you are going to reach using these media, basically. So that, and then of course, if that is the case, you want to maximize the influence that your using all these channels may have on your audience, basically on all those potential people that are gonna potentially buy your product, right? Next example is a transportation type of problem. So a company, imagine like Amazon has multiple warehouses in multiple locations, in different locations, and then they have demand coming from different regions. So there are demand regions and supply regions, right? So distribution centers or warehouses, as well as, so those are going to be considered as supply centers. And then there are places where they request the items. They are the recipient of the items, which I'm going to call them demand centers. So supply center, demand center. Now, in this question, in these type of problems, the decision that we want to make is how much or how many items to ship from a distribution center or a supply center to each customer or to each demand center. So this is the question, this is the decision that we want to make, how much item, how many items or how much product to ship from a supply center to any of those demand centers. And how do we evaluate the goodness of a set of actions is by, in this case, is by transportation cost. The objective here is to minimize the total transportation cost. All right. So like I said, usually in a linear programming, we are dealing with, we need to find decision variables, objective functions, and the set of constraints. And it's a very practical approach for finding the best set of action. And a lot of companies are doing it. Depending on the size of the company, you may actually be able to use the Excel solver that we use in this class, or you, depending again on the scale of the problem, Excel solver may not be enough. You may want to use a more sophisticated coding algorithm for finding the optimal decisions. In this course, at least in this video, our focus is going to be on formulation of linear optimization problems. So I'm going to actually show you two examples here. So I have one example written here. So imagine in a bakery, you have two types of cookies. So this is a very simple example. I just want to show you how important this tool is, the linear optimization, how important, how simple, and how powerful this tool can be in order actually to help us to make better decisions, better managerial decisions at the end of the day. So imagine we have two types of cookies in one bakery, and then each one of these cookies need, I'm just going to simplify the question. So we assume that the ingredients are only sugar and flour. So cookie type 1 and cookie type 2, each pound of cookie type 1 is made up of 0.6 pound of flour and 0.4 pound of sugar. Each pound of type 2 cookies is made up of 0.8 pound of flour and 0.2 pound of sugar. Each pound of type 1 cookie is sold, or the profit margin for each pound of cookie type 1 is $18, and the profit contribution for each pound of type 2 cookies is $20, right? So we have the profit margins, and we know how much ingredients each one of these two types need. We have limited inventory of flour and sugar currently. Let's say we have 60 pounds of flour currently in the stock, and we have 20 pounds of sugar currently available. So these are my limitations. If you think about that, these are actually my limitations here. So the question that we want to answer, the managerial decision that we want to make is as follows. We want to know how much of each type of cookies to produce in order to maximize the total profit. So I want you to pause the video and think about this one. Try to first formulate this problem for yourself, and also try to see if you can find the optimal solution. So I'm gonna go ahead and assign two variables, one for the amount of sugar that we want to produce, and one to the amount of flour that, the amount of type 1 cookie that we want to produce, and one for the amount of type 2 cookie that we want to produce. So the question is as follows: how much of each type of cookies to produce? So that would be my decision variables, and I'm gonna call it X1 and X2, the amount of type 1 cookie that I'm gonna produce, the amount of type 2 cookies that I'm gonna produce. I'm gonna just move this up a little bit and call this decisions. So I'm gonna assign one variable to each one, X1, X2. These are our unknowns, decision variables, the things that we want to decide about. So amount of type 1 cookie, amount of type 2 cookie. So this is what we want to decide about. Now, what is it that we want to optimize? We want to maximize profit. So objective function So we want to maximize what? Profit, total profit, and total profit. We know that for each pound of type 1 cookie, we're gonna make $18 in net profit, and we're gonna make $20 in net profit for each pound of type 2 cookies. So now my profit function. So for each pound of type 1 cookie, I'm making $18. But now if I decide to make X1 pounds of type 1 cookie, my total profit for producing X1 unit of cookie 1, cookie type 1, would be 18 times X1. So I don't know yet how much I'm gonna produce from type 1 cookie. For each pound, I'm gonna get 18. So at the end of the day, after that I produce X1, how much profit I'm gonna make? 18 times X1 for making X1 unit, X1 pounds of type 1 cookie. Plus, same thing for type 2. I'm making $20 per pound of type 2 cookies, and I'm actually making X2 pounds of type 2. So 20 times X2 would be the total profit coming from type 2 cookies. All right? So that is my objective function. So now I know what my decisions are. What are the things that I want to decide about? I assigned one decision variable to each one decision variable. So these are called decision variables. And then I formulated my objective function, the thing that I care about the most, the factor that I use to evaluate my decision. How do I say if my decisions, if my basically my decision about the amount of production of different types of cookies is good or bad? How do I say which decision is the best decision? By comparing the profit, their profit. So this is how I evaluate. So that's why I call it objective function. We want to maximize the profit. Now, it's not just the objective function that we should actually care about. Other than the objective function would be the constraints. So we should, the decision that we make should be realistic, right? So taking care of the constraints, considering the constraint, will make sure that we are not actually making some unreasonable decisions, right? So unfeasible or infeasible decisions. We want to actually, our decisions, we want to be reasonable. We want them to be feasible, possible to implement. So I have two constraints. I have two ingredients. Each ingredient, we have limited amount for each one of them. So I have flour and sugar. These are my constraint. These are my ingredients. For flour, the amount that I need, the amount that I'm gonna be needing for production of X1 unit of type 1 cookie and X2 units of type 2 cookie should be less than or equal to 60, right? So I'm just gonna write it here, amount needed should be less than or equal to amount available. So that's the logic of my constraints. I cannot use more than the amount that I have available in inventory, in stock, right? So I just need to make sure that my consumption of ingredient is within the feasible range. It's not gonna exceed the amount of inventory that is available. So how much flour do I need for production of X1 pounds of type 1 cookie and X2 pounds of type 2 cookies? If I just go back to the question here, I said for each pound of, I'm just looking at flour here. For each pound of type 1 cookie, I need 0.6 pounds of flour. So now I'm making x1 pounds of type 1 cookie. So how much flour do I need for x1 pounds of type 1? 0.6 times x1. How much flour do I need for baking x2 pounds of type 2 cookies? 0.8 times, so 0.8 flour per 1 pound of type 2 cookies. But now that I'm making x2 pounds of type 2 cookies, I just need to multiply 0.8 by x2. So indeed, the amount that I need is going to be 0.6 times x1 plus 0.8 times x2. So this is the amount that I have, 0.6 times x1 plus 0.8 times x2. So this is the total amount that I need, and this should be less than or equal to 60. With the same logic, with the same reasoning, I can write 0.4 times x1 plus 0.2 times x2 less than or equal to 20. So for sugar, for each pound of type 1 cookie, I need 0.4 pounds of sugar. For each pound of type 2 cookies, I need 0.2 pounds of sugar again. So 0.4 times x1 plus 0.2 times x2 would be the amount that I need to consume for making x1 and x2 pounds of type 1 and type 2 cookies. And that cannot exceed 20 because 20 is my limit for here. 20 is my current inventory. I cannot exceed 20. So now I actually define my decision variables. I have my defined my objective function, the profit, total profit, based on my decision variables. So now, I mean, I can change these values and then I get the profit, the dollar value of the dollar profit of my decisions, right? So you just change X1 and X2, it's gonna tell you how much profit you're gonna make. But in order for X1 and X2 to be feasible, to be possible, you need to, X1 and X2 should satisfy both of these constraints. Both of these constraints should be satisfied for X1 and X2 to be feasible values, to be possible to implement. One last thing is called non-negativity. Non-negativity constraint, and that means the amount of production X1 and X2 cannot be negative. They can be zero if the solution suggests they can be zero, but they cannot be negative. They can be positive, they can be zero, but they can't be negative. So what we just did is the formulation of the problem, defining the decisions, defining the objective function as objective as a function of decision variable, and then defining the constraints in terms of the decision variables again, and then the non-negativity constraint. And just note here that objective function is linear, so the power is 1, right? So the maximum power of decision variables that I see in this function is 1. And that's why I call this one a linear function. Same thing here. So I don't see, if you see x squared, that's not linear. If you see square root of x, that's not linear. If you see 1 over x, for example, that's not linear. But if you have a constant value times a decision variable plus another constant value times another decision variable that is a linear function, right? So that's one example. I'm gonna get back to these slides here and quickly review another example, a simple maximization problem on this slide. So we're just gonna go over the definition, the details of the question, and then we're gonna see how we can formulate this problem again using the same logic, defining the decision variables, defining the objective function, deciding whether it's going to be maximized or minimized, and then defining the constraints, including the non-negativity constraint. If you do all these steps, that would give you the formulation of a LP problem. And in order to be able to solve an LP problem, a linear optimization problem, you need to have the formulation. You need to formulate the problem mathematically the way that we just did here. So the next example, we have a manufacturer of a golf equipment and supplies. So this is a production scheduling type of problem. And a very simple one. We just have two products. We have, let me just go to the next slide. We have standard bag. They're making golf bags. There are two types of product, standard bags and deluxe bags. And operation involved in manufacturing of a golf bag includes cutting and dyeing, sewing, finishing, inspection, and packaging. So 4 stages. And then we have the unit time in each one of these departments for each unit of bag. And for both types, for standard and deluxe. For each standard type bag, standard bag that you produce, you need 7 by 10 hours from cutting and dyeing department, half an hour from sewing department, 1 hour from finishing department, 1/10 of an hour from inspection and packaging department. So for each standard bag, this is the schedule. This is the amount of time that you need from each one of these departments. For each deluxe bag, the same thing. I mean, the numbers are different, but you have the per unit of deluxe bag time in each one of these departments. So the time that each deluxe bag, each unit of deluxe bag takes from each one of these departments. So we have the numbers here, right? And the number of hours that we have from each one of these departments is limited. So we have limited capacity here. So it's a production scheduling problem with limited capacity. 630 hours of cutting and dyeing. And it's up to you to decide to basically how to allocate this time between standard and deluxe bags, right? So you have the per bag time that you need from cutting and dyeing for each one of those standard and deluxe bag. Now it's up to you to decide how to allocate this time. And in order to actually evaluate our decision, evaluate our production scheduling plan, we have the profit contribution of each bag. We know that each standard bag is going to make $10 profit contribution per unit, and each unit of deluxe bag is going to make $9 net profit at the end of the day. All right. So now, how do we formulate this problem? We want to develop a mathematical model of the company, to determine the number of standard bags and the number of deluxe bags to produce in order to maximize the total profit contribution. So it's a maximization problem. It's a maximization LP problem. So here we want to formulate the problem. So here we had the description. We had the problem in words. Now we want to basically translate the verbal statement of the problem into mathematical statement. And when I'm talking about mathematical statement, we need the notation for decision variables. We need the objective function in terms of decision variables. And we also need constraints in linear forms. Each constraint should have a left-hand side, a right-hand side, and a sign in between, right? So similar to what we just saw here. So each constraint has a left-hand side, a sign for the constraint, and right-hand side. So this is a less than or equal type of constraint. Left-hand side is a linear function, right-hand side is a fixed value, is a constant, right? Going back here and continuing with our problem. So general guidelines for problem formulation. The first step is really to understand the verbal statement. Understand exactly what is it that you want to decide about, what is it that you want to maximize or minimize, and what are your considerations, what are your constraints that may actually change your decision, may make your decision feasible or infeasible. Then describe the objective, describe the constraints, define the decision variables, and then start writing the objective and constraint in terms of decision variables in mathematical language, basically mathematical format. So in this specific question, in this production scheduling type of question, we had four departments, and we have limitation on each one of these departments. So we have cutting and dyeing. The number of hours available is limited. The number of hours for sewing department is limited. The number of hours of finishing and inspection and packaging. So 4 departments, 4 limitations, and 4 constraints that should be defined for this problem. So let's get started. For decision variables, we have 2 decisions to make: the number of standard bags to produce, the number of deluxe bags to produce. So S and D, right? So we can call them S for standard, D for deluxe bag. And then the next step, writing down the objective function. Objective function, we said there's $10 profit contribution for each standard bag and $9 profit contribution for each deluxe bag. So in total, now that we're making S unit of standard bag, 10 times S would be the total profit coming from standard bag. $9 for each deluxe bag. Now that we're making D units, 9 times D, that would be the total profit coming from deluxe bag. And then if we just add them, that would be our total profit contribution coming from the total production plan. 10S plus 9D, that's our objective function, right? And we want to maximize this. We want to maximize the objective function. And for the constraints, the logic is that the number of hours that we need to use should be less than or equal to the number of hours that are available from each department, all right? So we knew that for each standard bag, we needed 7 divided by 10 hours of cutting and dyeing. And then for each deluxe bag, we needed 1 hour of cutting and dyeing, right? So now 7 divided by 10 times S plus 1 times D, that is the total time that you need for producing S unit of standard bags and D units of deluxe bags. And that should be less than or equal to total amount of time available from cutting and dyeing department, which is 630. So that way you can define the constraint 1, constraint for cutting and dyeing. With the same logic, you can write down the constraint for sewing and the other two, finishing and inspection and packaging, right? And then at the end, we have the non-negativity constraint, meaning that the number of production cannot be negative. You either produce or do not produce. If you don't produce, they're going to be zero. Either S or D or both of them are going to take zero. If you start producing, they're going to take positive values. And in this specific case, they're going to actually take integer numbers. So they can't really take continuous number, any like decimal numbers, right? So they have to be integer, but we're gonna skip that for now. So overall, this is going to be the formulation. We have decision variables S and D. The objective function is profit. We want to maximize the objective function subject to the set of constraints. We define 4 main constraints, one for each department: cutting and dyeing, sewing, finishing, inspection, and packaging. The number of hours used should be less than or equal to the number of hours available, the right-hand side. And then we have the non-negativity constraints. So like I said, in this formulation, everything is in linear function. Linear function is a mathematical function in which each variable appears in a separate term and is raised to the first power. So you can't have x1 times x2 or s times d. They have to be separate, and the power of each one should be exactly equal to 1. It's okay to have constant values. So you may have power of 0, which, I mean, having a constant value is indeed having the decision variables in power 0. So you don't need to really worry about that. So having decision variables in separate terms and in with power 1. So this is how we identify linear forms.